Okay. Yeah, so this is going to be the presentation order. And I'll make sure to post this on Canvas as well. So this was just chosen randomly. I think last time we said we might leave it flexible for people who want to like volunteer earlier, and that's fine. Like if you want to swap with someone, that's fine. Just go ahead and talk to them and then let me know if you agree. Otherwise, we're just gonna go with this randomly chosen order. And so the first presentations are going to be next week, starting on Wednesday. Monday is going to be a holiday, so we actually don't have any class, which actually means today is going to be the last lecture of material. The rest of the class will be dedicated to presentations. Yeah, and then the project presentation slides will be due for everybody at the beginning of class next Wednesday. So do make sure that you get your presentation submitted, even if you are presenting on the later date. Great. Any questions about presentations and the project? Or concerns? Okay. Sounds like everyone's got everything in order. So we're going to have flawless presentations next week. All right. So since it is the final lecture, I'm actually not going to do new material, which means we may have a slightly shorter lecture today. But we did learn quite a bit of material over the quarter. So I wanted to kind of do a little bit of review and give kind of an overview and perspective about how we can apply everything that we learned in, I guess, a more sort of generalized framework. Okay, so data analysis. Oftentimes, I think, especially when this class was originally formed, there was kind of an expectation that this was kind of a follow-on class to the ECI, I think 254 or 253. It's the like intro to R class that used to be taught by Deb Niemeyer. That this would be kind of a follow-on to that. But I think over the years, I think fewer and fewer people have been taking that prior to this course, which is fine. They're kind of disconnected, but I think one of the big things that's emphasized in that class that we probably cover a lot less is kind of understanding and summarizing and examining the sort of data. So we kind of jumped right into creating models to do data analysis. But even prior to that, I think one of the big things that you'll always want to do is really to examine the data. So this would be doing things like investigate the distribution of data, really understanding really understanding kind of what the data looks like, how it could be distributed, how that kind of relates to your ultimate, regression models, or, clustering models. I think that it's often a really big mistake to kind of just look at the data, or not to really look at the data carefully, just kind of load it in and start running models. I think that delving into, and even sort of from a visual perspective, what the data looks like can really help to guide you in creating the models, which ones tend to, what types of models that you should be applying, and how it relates ultimately to the results and interpretation of results. So data examination, I think, is very crucial. So looking at the basic relationships between variables. There's lots of different simple ways to do this. You could create a correlation matrix. You could do scatter plots of, two variables together, look at how, if they're sort of randomly associated with them, or if there's like a very clear trend. This can be like a really obvious way to think about the functional fit of data. And obviously this is somewhat of a simplification, but like if you had, for example, data that looks like fairly linear, versus if you had data that looks, non-linear. If you kind of just run a linear regression, right, you may be missing really sort of obvious details that you could sort of glean from a higher level investigation of the data. And doing all of this also helps to develop hypotheses about the data and your model. Sometimes you may come into a particular project or problem with some idea of exactly what you want to test in mind, or how you want to structure the model based off of like other research that's been done, or even intuition of some kind. But sometimes you may be coming into a new data set where you don't have necessarily a good idea about some of the underlying relationships between variables. And again, so really diving in and examining the data can help to get some ideas about how to structure the model, how to set up relationships between variables, and that sort of thing. And so this whole examine the data section isn't something that we've covered in a huge amount of detail in this particular class, but I want to make sure that as we go through the rest of the sort of modeling stuff, that you don't overlook this first step, which I think is very crucial to doing your data analysis. Okay.
Alan, I just had a
Yes.
quick, it's a bit random, but I
Uh-huh.
was wondering, is there any role of interaction terms in predictive models? We did that in inference models, but not in the predictive ones.
Yeah. Um, so in predictive models, um, the it's actually the treatment for interaction is fairly similar in that um, it's difficult to include all combinations of prediction predictive variable, or sorry, it's difficult to include all combinations of interaction variables because of how sort of quickly um, it it explodes when we're thinking about like combinations of variables. So if you have like uh, a dozen variables, the number of combinations that you could have to interact all of those variables is already uh, very, very, very large compared to kind of just the base set of variables. Um, and for that reason, in a lot of the predictive models, you would only really think about including those if you have some underlying intuition um, about some kind of nonlinear relationship um, that is a result of that interaction. What I will say, however, is that as we have got onto sort of more complex, like semi-parametric and non-parametric models, so like if you think about like the splines, the spline models, the kernels, some of the neural networks, because they are so inherently flexible, like you can the tuning parameters that we use, right, that they're always talking about to increase the flexibility. Um, Oftentimes, those are more than enough to capture um, any sort of relationship between your x's and your y's, so that it's not really necessary to include interaction variables, interaction terms, uh, because you already have enough degrees of freedom to get a really good fit. And in fact, um, inclusion of the interaction variables in those sorts of models um, really aren't going to help um, with the predictions because the flexibility already puts you into the realm of possibly overfitting. And so as you add more essentially degrees of freedom with these additional variables, then it's not, yeah, it becomes somewhat redundant. It is possible to include them, but more often than not, you don't need to. I think where that particular question becomes very interesting is for hybrid models, um, especially for something like the general additive model, where you uh, are doing some kind of like smoothing fit curve, right? So you have like the splines for the individual variables so that you can look at the relationship. Um, and in that case, um, there is potential to add in the interaction variables, but you wouldn't want to just include all of them. It would again be kind of based on intuition.
Thank you.
Yeah. Okay. So number 2, so developing a model and learning from the data. So this is really kind of generalization of the suite of models that we talk about. So you've got supervised learning and unsupervised learning. And the main distinction, right, is that in supervised learning, you have an explanatory variable, or sorry, not explanatory, response variable. Your y, and here you have no response variable. So in the unsupervised learning, the methods that we've talked about are clustering, and this was k-means clustering. And hierarchical, or agglomerative clustering. And then the other unsupervised learning, which we didn't really cover, principal components analysis, which is closely related to the principal components regression, but instead of looking at the dimension reduction as it relates to some kind of response variable, it's only doing kind of the slicing of the dimensions from all of the variables without necessarily a contribution to a specific outcome. And then we have a whole host of models that we talk about in supervised learning. And actually from 2 lectures ago, I think the GLM, so this is the generalized linear models, is a nice framework for discussing the types of regression models that kind of exist in the linear and parameters space. And so let's talk about that. So the first thing is how we're going to categorize our x's and our y's. So you have continuous explanatory variables as well as discrete. And so for basically all of the models that we've discussed, they can handle both of these types of variables. For discrete, we are usually doing this with dummy variables, and then with continuous, it's just kind of as we've discussed throughout the class, as being able to treat that response is continuous between your X and your Y. And then for your Y, you have also continuous response variables as well as discrete response variables. And the way that the GLM kind of describes handling sort of different combinations of your X's and Y's has to do with the relationship between your X and your Y's. And so kind of the most basic one, right, is when you have linear. And so this assumes that X is anything and Y is continuous. And then we had our logistic models. And this one, we have X is anything and Y is discrete. Within the GLM framework, there are also a couple of other details, right? So how is your Y distributed? In the continuous, a lot of the times we assume that it's normal, and then in the discrete, you know, if it's if you have like two outcomes, that could be just like a binomial distribution. And so more generally, as you get to sort of more specific or complicated examples where your Y's may be distributed in a different way, or the relationship between your Y's and your X's are of a different form, then you would start to look at the specific types of models that we talked about in that lecture to apply to analyze your data. But this is kind of at a high level how we're talking about modeling these combinations of X's and Y's. Okay. So variable selection. How can I tell what variables that I want to put into the model? At what point am I confident that I've reduced some of the fundamental bias in the model, and what point do you start worrying about things like overfitting the model? And so we talked about 3 general techniques to do this. So one is subset selection. 2, regularization. And then 3 is dimension reduction. Okay, and so there are plenty examples of specific models that are going to help you do this. And these can be kind of contained within the context of something like a linear regression or a logistic regression. So this could be like stepwise regression. So you could have step forward, step backward. Regularization, we talked about a number of different models. Let's see, we have the lasso and ridge regressions. What else was there? The smooth spline is essentially like a form of regularization. What else do we have? In the last class, when we talked about convolutional neural networks, is essentially also a form of regularization. For dimension reduction, we talked about PCR. Actually, I'll write it out. So principal components regression. We also had linear discriminant analysis. That's another form of dimension reduction, kind of analogous for explanatory variables where you have discrete outcomes. Okay. And let's see. Oops. So model diagnostics. This was a little bit earlier in the class, but we talked about different ways that we could determine essentially how good your model is, what things that you might want to watch out for. So residuals, yeah, in my opinion, one of the sort of most important ones that really help to tell you whether or not there is bias that exists in your model and the fit. So significance of coefficients, things like R squared, mean squared error is one that we have kind of continuously relied upon, particularly in some of the predictive models. There's also the outlier analysis. So this is things like leverage, Cook's distance. Okay, and so importantly, remember that you should always kind of remember what these diagnoses are telling you, and really what they mean fundamentally. I tend to see that this issue with not only students but even like researchers and faculty, where you treat any one particular diagnostic device as kind of an end all for how good a model is, right? Each of these things are telling you one specific thing about your model, and not any single one of these is just going to be able to tell you that your model is good or bad. So keep that in mind. I think it's probably one of the most common things that I see when people are employing data analysis and maybe defending their models. They just say, hey, okay, look, I have a bunch of variables that are significant and therefore my model is good. And that's not what this means, right? You know, you could have a model with 10 variables and they're all super significant and you think your model's really good, but if you looked at the residuals, your model could be super biased, right? And so again, these metrics mean something and don't overextend their meaning as a way of justifying how good your model is. Okay, I see Maha, you've raised your hand. You have a question?
Yeah, I was just wondering, like, for data science papers that are published,
Yep.
do you usually have more than one model and then you're comparing the MSEs? Because the kind of papers we usually see in economics, they'll just have one model and they'll report the R squared, which is easy to interpret because it's standardized, but the MSE is not standardized, right? So I was wondering, like, do data science papers do that? They have a lot of models and then they compare the MSE?
Yeah. And I would kind of echo what you're saying, is that you definitely see you definitely see specific diagnosis devices being used differently and applied differently within specific fields. So it is a lot more common to see, for example, mean squared error measurements as a diagnosis device in like machine learning and statistics. And oftentimes what they'll be showing is like a whole suite of different models. And then they're comparing a bunch of MSEs, and then they take the one with the lowest MSE and say, okay, this is like the best model. Because you're oftentimes working with a lot sort of fewer variables and thereby, you know, fewer possible models. I would say in like econometrics, it's less common, definitely much less common to see something like mean squared error. Part of it is also due to the fact that in that field, I would say there's less exploration of things like functional fit. Usually it's just going to be some variation of some linear models. And because of that, they care a lot less about the model comparison and more about the specific relationships between certain variables, that therefore they don't care so much about the mean squared error. And that's not to say that one approach is necessarily better than the other. They essentially care about different things, right? So to give you maybe a more concrete example of this, let's say that you're more in the like econ world, and you really want to determine the relationship between between your X and your Y, and you put in a whole lot of effort to essentially try and capture and measure that relationship, but you don't actually care so much about getting an accurate like prediction of your Y, as long as you've been able to demonstrate that you have measured the relationship correctly. And because of that, you may have a like fairly large, a relatively larger like mean squared error compared to something where you throw in a whole bunch of other variables. And in that sense, like if you were to try and improve the model's MSE, you may do so, but at the cost of muddling the relationship between your X and your Y. And for that reason, you know, the use of like an MSE metric might be like a lot less compelling for you. And that's why having a good understanding of like the model diagnostics plays such an important role in the sort of framing of your model as a whole, because you really want to make sure that you understand like which diagnosis devices make the most sense in the context of the problem that you're trying to address. Okay, so I hope that answers your question.
Yeah, definitely. And just to add to that, like I experienced this last quarter. I was taking a course on R, and one of the teachers was a data scientist and the other one was an economist.
Yep.
So really have different approaches, even in the way they treat their variables. Like the economist would actually be offended that you dropped a significant variable that was kind of classified as significant, but later not. So yeah.
Yeah. That's a great example, actually. So like, because I care about the relationship, I say, hey, like I want, let's say your X1 has like a really nice statistical or statistically significant value, and you determine that it's got this kind of relationship with Y, and you've done all the like proper like IV procedures to do that. And so from an economist perspective, you're like, great, I really like this because I understand this relationship between X1 and Y. But from like someone who's doing machine learning, I might say, yeah, but your predictions are terrible. I'm going to throw in X2, X3, X4, even though they're all like really collinear with your X1, which is like a big no-no, right? You don't want to put in variables that are collinear if you're doing inference. But I don't care about the relationship between the X's and the Y's. Just throw in all the variables and get like a good prediction. Yeah, and so that's exactly the type of case where, you know, you are thinking about specific diagnoses, MSE versus, you know, significance of coefficients. Yeah, and again, this is like I've operated kind of on both sides of that. So, you know, this is not to say one way is better than the other, but like having a firm understanding of what all these mean is really going to help you like understand what to do in different contexts. Great. So five. Bias, variance, trade-off. So I guess even though we talk mainly about this MSE in the prediction world, even in inference, I think this is a really important concept, especially because at the end of the day, you will really want to think about reducing your error as much as possible. Part of this, you know, even in the inference world, because it's not really possible to totally separate correlations in your error term with your explanatory variables. That's why it's kind of fundamentally important to still try and reduce your errors as much as possible. And not only that, it can also help in solidifying some of the relationships between your x's and your y's. So model complexity, we've talked about this. As your model increases in sort of quote unquote complexity, you reduce your bias, but you also increase your variance. And so your total error will look something like this. And we basically want to reduce the total error as much as possible. How do we do this? Cross-validation. So this is a pretty fundamental technique that can be applied to essentially any this can be applied to any model, right? Generally, from a predictive standpoint, doing this as much as possible is going to help improve out-of-sample predictive ability of your model. From an inference standpoint, I think that this is also a really good way of making sure that this relationship that you've kind of hypothesized between your x's of interest and your y will actually lead to the outcomes that you see in reality, in other words, in things that happen out of sample. And we've seen how this fundamental principle is applied through a whole host of ideas for variable selection and to prevent overfitting, right? And so if we go back to our techniques here in our variable selection, for example, stepwise regression, we select based off of like the AIC, BIC, or adjusted R squared. It's the same kind of principle where you are penalizing having more variables, and the reason you do that penalty is because of the bias variance trade-off. In regularization, we have that tuning parameter with the modification term that gives that penalty to coefficients, right? For having lots of coefficients that don't really do anything and they get penalized down to 0. That again is determined by your bias variance trade-off. And that's kind of the same as the tuning parameter in the smooth spline. And then in the neural networks, when we do gradient descent and figure out the weights of our model, it's the same kind of feedback loop where it's essentially looking at the lowest at the lowest out of sample, right? The testing, mean squared error, using this principle of bias variance trade-off. So this concept is central to a lot of the modeling approaches that we've taken. Okay.
Alan,
Yes.
do we usually perform multiple variable selection process, or is there any like specific data set that could better use the specific variable selection process too? I mean, we have three, we have before. Like, do we usually like try to perform at all, or just pick like one of them? How?
Okay, wait, sorry. So I'm not sure I heard you correctly, but are you talking about in the stepwise selection?
Yeah,
The
and number three, we have like the variable selection process, right?
number 3. Yeah. So
Yeah,
these.
there are three process there, and then do we
Mhm.
just pick one or try to use all of them, or?
I see. I see. Yeah, that's a good question. I guess what I would say about this is that these regression models are not quite meant to address the same types of problems. So I should say like a principal components regression, like that is often applied to problems that have an enormous number of variables, where it would be problematic to even do something like a stepwise regression. And in that case, it's also has no ability to do inference. And so there are these, I guess, sets of criteria that may help you determine what type of model that you would use, especially in the context of like variable selection. So for example, the PCR, that one that I'm talking about is, okay, if I have hundreds or thousands of variables and I don't care about inference, then I'm going to use like principal components regression. If I am doing, if I have, if I'm really concerned with inference, and I may have a reasonable number of variables, then that's where you might care about doing a stepwise or a lasso or ridge regression. If you are really worried about the like functional fit, or you don't want to be operating with like a linear relationship, a directly linear relationship between your x's and your y's, and you don't want to mess with like having complex polynomials or interactions, you could do like a smooth spline. So if you're in the world of like prediction, right? And so there are different contexts to apply specific types of models. And the specifics of which, I think if you maybe like review some of the individual lectures, like we try to contextualize the example problems with types of problems that you would actually use these sorts of models. And so, no, I wouldn't say like if I had some data set and I wanted to be really robust, I wouldn't just do a stepwise and a lasso ridge and a smooth spline and a PCR. Like it kind of depends on the type of data that you have and on what you're trying to achieve through the modeling. Okay. Actually, what number am I on? 6. So, inference versus prediction. So we've been kind of hinting at this throughout the lecture. So inference cares primarily about relationship, about determining the relationship between x's and y's, whereas prediction cares primarily about accurately predicting y's given data. And that drives a lot of the fundamental decision making behind some of the modeling decisions and choices. So for example, these tend to be parametric or semi-parametric. Whereas prediction tends to be semi-parametric or non-parametric. And what this means is that you are making some assumptions about the functional relationship between your x's and your y's versus trying to shy away from those assumptions in the predictive sense. And so this might be like a linear relationships. And the reason why you would do that, right, is because if I do like a linear model, my betas simply describe a linear relationship between my x's and my y's, and that's very easy to interpret. So this would be something like having a model fit like that, which I can describe with a single number, versus having a fit that might look like that, which would be a lot more difficult to kind of relate in a straightforward way. In one of the things that I think is important to take away from this is that, you know, if you're operating in the realm of inference, that it's often a good idea to check whether or not the linear relationship is a good is a good functional fit. So one of the ways you could do this is like you could look at residuals and see if they're biased, and one possible reason for that is because that linear relationship might not accurately be describing it. And then actually on the homework that you guys are submitting today, one of the things that I had you look at was with a general additive model, when you look at the plots of the fits, which ones look fairly reasonable to assume as a line, and which ones look kind of particularly different from a line. And I think that's like a pretty simple thing that you could always do to check whether or not the linear relationship makes sense. And so if you're ever publishing like an econometric model of your data, I think it would always behoove you to just quickly run a general additive model with smoothings, with splines for all of your explanatory variables, and just see, hey, do these all look like lines? If there's anything that looks a little bit crazier, then you might want to think about adding in or modifying the variable in some way so that you can linearize it, and so that the linear model is still doing a relatively good job of fitting to the data. So for causality, this is, or causal inference, we'll say. This is particularly difficult. We talked about instrumental variables. Instrumental variable regression. And then for controlling random effects, we had one half of a lecture where we talked about mixed models. And both of these are really, again, firmly rooted in kind of the inference side of things. On the predictive side, we started to add in functional fit or functional form flexibility through splines, through kernel regression, and then we delved into ways that you can really introduce lots of flexibility with neural networks. So this includes feed forward, also known as mixed multi-layer perceptrons, and we also talked about last time convolutional neural networks that are applied for a specific class of problems, image classification usually, but are good for generally like grid-based data. Okay. Any questions so far? Okay, and so I guess kind of the last thing that I'll leave us with is interpreting and contextualizing your results. So what do the statistics say and what do they not say? So this is kind of rehashing what I was saying earlier, specifically with the model diagnostics, but broadly over the application of the different types of models, having a good understanding of what the models are doing, what you're trying to estimate, how they relate to the outcomes of interest. I think these will all help to ensure that you are not overextending the reach of what a model is actually telling you. Why is it important? What relevant things does it tell us? Yeah, and this this is, I think, a really common type of I don't even want to say necessarily a mistake that people are making, but you're going to get, sometimes you'll get so involved in the modeling and ingrained in it, you need to kind of step back and remember that not everyone is kind of operating necessarily at the same level as you and understanding in both the data and in the modeling. So you can say, you know, I've gone to talks where people say, oh, look, our model has this MSE of like 16,000, blah, blah, blah. Isn't that amazing? And it's like, well, what does that mean? Like, what are you trying to tell us with the model? Like, what are you actually comparing the MSE to? Or, you know, you may go to a different talk and someone just says, okay, this variable is statistically significant at the 1% level. And then that means this whole thing is amazing, but like, you know, tell us an explanation of the actual relationship that you care about, and not just focusing on specific numbers that are coming out of the model. Yeah, and then know your audience. And oftentimes, unfortunately, that means that a lot of the like good work that you might be doing goes somewhat unnoticed. You may spend a whole bunch of time doing a bunch of like different models and trying to do these robustness checks, looking at a bunch of diagnoses, but like for certain types of audiences, no one's going to want to see, you know, all of your residual results and, you know, giant tables of, you know, coefficients, for example. Sometimes you would just have to say, hey, trust me, we did a lot of these tests to make sure that the model is good. But here are kind of the general results and what they mean. Whereas, you know, if you are presenting to a more like statistically savvy audience, then you might go into the techniques that you use, like, oh, I did a k-fold cross-validation with this number of folds and this sampling procedure and so on and so forth, right? So I think it's always a good idea to think about how to talk about your results based off of who you are speaking to. Yeah, okay. And so I think that covers most of my, I think, words of wisdom or guidance that I have on the subject. And I think we've covered most of the things that I wanted to chat about. So yeah, thanks everyone for attending the class and listening to me ramble on Zoom. Yeah, I look forward to the project presentations and the rest of class, and for all of this stuff that that we've learned throughout the class, and as you potentially apply this to your research, definitely you know, feel free to reach out if you need any help or assistance, and definitely feel free to stop by eventually when the campus opens up. I've met a good chunk of you guys in person, but definitely more than half of you I have yet to meet in person. So definitely it would be great to meet you at some point. Yeah, other than that, thanks a lot for attending, and I'll do our same thing as always. I'll stick around a couple minutes for questions if anyone has any.